Hello, I'm Dr. Steve Warner, and today I'm going to talk about the integers, primes, factors, and multiples. The integers are the counting numbers together with their negatives. So we have 0, 1, 2, 3, 4, and so on, and going the other way, -1, -2, -3, and so on. The positive integers are just the positive numbers from this list, 1, 2, 3, 4, and so on. A prime number is a positive integer that has exactly two factors, and those factors would be 1 and itself. So here's a list of some of the first few prime numbers: 2, 3, 5, 7, 11, 13, 17, and so on. Note that 1 is not a prime number because it only has one factor. To see a couple of numbers that are not prime, for example, 4 is not prime because it's 2 times 2. 6 is not prime because it's 2 times 3. 9 is not prime because it's 3 times 3. The fundamental theorem of arithmetic says that every integer greater than 1 can be written uniquely as a product of primes. I put the word uniquely in quotes because it's not entirely accurate. For example, the number 6 can be written as 2 times 3, but it could also be written as 3 times 2. So it can be written uniquely, but only up to the order in which we write the factors. So what we do to make it really unique is we always agree to write the prime factorization in what's called canonical form. And that would be this one. The canonical form is when we write the prime numbers in increasing order. Let's look at another example. Let's get the prime factorization of 18 in canonical form. To do this, let's draw a little factor tree. So 18 can be written as 2 times 9. Since 2 is prime, I'm going to circle it. 9 is not prime, so I'm going to continue to factor it further as 3 times 3. And 3 is prime, so I will go ahead and circle those. So the prime factorization in canonical form is 2 times 3 times 3. Remember, canonical form means we write in increasing order of primes. 2 first, followed by 3. When we have repeated primes, to write it a little more simply, we'll use an exponent. So we'll write 18 as 2 times 3 squared. I just want to point out that there are other ways to factor the number 18, such as we could start instead by writing 18 as 3 times 6, circle the 3 because it's prime, and then 6 we could write as 2 times 3. Both of those are prime. Notice that we still get 2 times 3 times 3. Again, the fundamental theorem of arithmetic says that the prime factorization is unique, but we got there in very different ways. Notice the intermediate step is very different here. But we always get the same result at the end. The greatest common factor of a set of positive integers is the largest positive integer that each integer in the set is divisible by. And the least common multiple, or the LCM of a set of positive integers, is the smallest positive integer that is divisible by each integer in this set. If you find these definitions confusing, that's okay. We're going to do some examples that should clear it up. So let's start by finding the GCF, greatest common factor, and LCM, the least common multiple, of the numbers 9 and 15. I'm going to do this a few different ways. So here's the first way. Let's start with the GCF. I'm going to start by writing all the factors of 9. So those are 1 is a factor of 9, 3 is a factor of 9, and 9 is a factor of 9. And let's also write the factors of 15. 1, 3, 5, and 15. Now I'm going to circle the common factors. 1 and 3 are common factors to both 9 and 15. So the greatest common factor is the bigger of those numbers, which is 3. Now for the least common multiple, I'm going to start writing the multiples of 15, and I'm going to continue writing the multiples of 15 until I find a multiple of 9. 45 is the first multiple of 15 that's also a multiple of 9. Okay, it's a multiple of 15 because it's equal to 15 times 3, and it's a multiple of 9 because it's equal to 9 times 5. So the least common multiple of 9 and 15 is 45. Let's look at another method. A second way to do this is to get the prime factorizations of both 9 and 15. So let's make factor trees for each of these. Okay, so we see that 9 is equal to 3 squared, and 15 is equal to 3 times 5. Now, to compute the GCF, we take the lowest power of each prime. The lowest power of 3 is 3, and since 5 does not appear in this one, we do not take any power of 5. So the GCF is simply 3. For the LCM, we take the highest power of each prime. The highest power of 3 is 3 squared, and the highest power of 5 is 5. So the LCM is 3 squared times 5, which multiplies to 45. Now, if you're having trouble seeing the highest and lowest powers here, it might help to fill in the missing exponents. For example, 15 is 3 times 5. That could also be written as 3 to the 1 times 5 to the 1. And 9 is 3 squared. Since there's a 5 in the 15, or a 5 in the prime factorization of 15, we might want to add in the 5 into the prime factorization of 9 with an exponent of 0. Okay, so now you can clearly see that the lowest power of 3 is 3 to the 1, and the lowest power of 5 is 5 to the 0. And remember, anything to the 0 power is just 1. Similarly, we could see that the highest power of 3 is 3 squared, and the highest power of 5 is 5 to the 1, giving us the LCM. One last method for finding GCF and LCM of two numbers is to simply use your graphing calculator. On the TI-84, you can press the Math button, scroll right to NUM, and then you can select GCD. Notice that GCD stands for greatest common divisor. GCF stands for greatest common factor. They mean exactly the same thing. After you select GCD, you just put in 9, 15, hit enter, and you will get an output of 3. Similarly, for the LCM, Math menu, scroll to number, and this time you're going to select LCM, input 9, 15, Press enter, and you get an output of 45. Let's go ahead and do a slightly more tedious example. We'll find the GCF and LCM of 100 and 270. Note that we could use the calculator method. Since that one's pretty straightforward, I'm going to do it by prime factorizations. So let me draw factor trees for 100 and 270. So 100 is 10 times 10, and that's 2 times 5, 2 times 5. Those are all prime, so that 100 is 2 squared times 5 squared. 270, let's see, we could write that as 10 times 27. 10 is 2 times 5. 27 is 3 times 9. And 9 is 3 times 3. So we have that 270 is equal to 2 to the 1 times 3 cubed times 5. So for the GCF, we take the lowest power of each prime, which is 2 times 5. Note that we don't use the 3 because 3 is not a factor of 100. So the GCF is 10. For the LCM, we take the highest power of each prime, so that's 2 squared times 3 cubed times 5 squared, and that comes out to 2700. Remember, if you're confused by the missing primes, you could always fill in the missing ones with a power of 0, and you could also throw in the power of 1 for the ones that only appear once. Now let's try a typical multiple choice question. What is the least positive integer divisible by the integers 3, 7, and 14? So this question is just asking for the least common multiple of 3, 7, and 14. We can do this using some of the methods we just learned, but since we have answer choices, I'm going to show you another way that works only for multiple choice questions. Since the word least appears in the problem, I'm going to start with the least answer choice and check if that number is divisible by 3, 7, and 14. But 28 is not divisible by 3. So the answer is not choice E. Let's try choice D next. 42 divided by 3 is 14. 42 divided by 7 is 6. And 42 divided by 14 is 3. Since all of these answers came out to integers, 42 is divisible by 3, 7, and 14, so the answer is choice D. If we do this one using our calculator, we have to adjust our strategy a little bit because for some reason the TI-84 calculator can only take 2 inputs at a time when computing the LCM. So to do this with your calculator, first compute the LCM of 3 and 7 to get 21, and then compute the LCM of 21, the answer we just got, together with 14, and that will give you 42. Once again, choice D. Okay, now let's try a more challenging question. The integer k is equal to m squared for some integer m. If k is divisible by 6 and 40, what is the smallest possible positive value of k? Okay, so in other words, we're looking for the smallest perfect square that is divisible by the least common multiple of 6 and 40. So let's start by finding the least common multiple of 6 and 40. And we're going to want the prime factorization of the least common multiple. So let's make factor trees for each of these. Hopefully you're comfortable doing this at this point. So notice that 6 is 2 times 3. 40 is 2 cubed times 5. And so the least common multiple is 2 cubed times 3 times 5. Now the integer k that we're looking for is the smallest perfect square divisible by 2 cubed times 3 times 5. To get the smallest such perfect square, we increase each of the exponents to be the first possible even number. So the answer is 2 to the 4th times 3 squared times 5 squared, which, when you put in your calculator, you will get 3,600.